let's then continue. So I start with the homework, and then we'll continue the discussion. So in the homework you had two problems, and the first one was standard problem. You had that pendulum, but now the pendulum is not oscillating, but instead it's rotating like this, right? And so its length is L, and it's rotating with around the cone with angle theta. And you were asked what is the velocity of the rotation. So actually the simplest way to do that is to use Newtonian mechanics, and you say that there are two forces acting on that bob. There is force mg, and there is force which is the force of tension of the little rope there. And so the sum of those two forces must be such that the total sum is pointing towards the center of the circle at which rotating, and that force must be equal acceleration mass of the bob times its acceleration. The acceleration is velocity squared divided by the r, which is the radius of the circle, right? And that from this triangle you see that radius equals L times sine theta, right? From this triangle. So that's your acceleration, and that must be equal to the sum of two forces, right? It's the forces are vectors, so they must sum up in such a way that the force is actually horizontal. It means that there must be two equations. The vertical forces, the vertical components must cancel each other, and what it means is that mg must be equal t times the cosine of this angle. Cosine of this angle is the same theta, so it's cosine theta. Right? That's the first equation, which ensures that the bob is not moving up and down. It just stays in the circle. And the second one is that the only force which has a horizontal component is t, and so in that horizontal component must be equal to v squared over r. So it must be t times sine theta here, right? So here we have all the equations which we can write actually all of them, right? It's all components of the forces and acceleration and everything. So now the only thing which you need to do is to substitute everything in, and what you will have then is m v squared divided by L sine theta. That this one equals now t, but t equals mg divided by cosine theta. So it's mg divided by cosine theta times sine theta. Right? Also from here your masses cancels out, and velocity squared equals lg times sine squared theta divided by cosine. Okay. Well, the velocity equals square root of lg divided by cosine theta, and everything is multiplied by sine theta. Right? That's the answer, and that's it. But you can also do a little bit more with the problem. And actually, I suggest you always try to figure out something else about the problems which you have always. So what you can do is to ask what is the frequency of the rotation, right? And the frequency of the rotation, that's it, that's the answer. I mean, it's something extra which you can do. The frequency equals 2 pi divided by the period of the rotation, right? Period of the rotation is how much time it takes for the bob to go all the way on the circle. So that time equals the length of the circle, it's 2 pi r divided by the velocity, right? So we already know the velocity R is, we know R is L times sine theta. So what you have here is 2 pi L times sine theta divided by velocity, right? But velocity also has sine theta there. So it cancels out, and what you have now is that this equals to 2 pi divided, the 2 pi is also cancelled, sorry. 2 pi is also cancelled out, and what you have is G divided by L times cosine theta squared. And that's the frequency of the rotation. And now you can actually see something which I don't know if it's surprising or not, but it's quite interesting thing to do to know is that if cosine, if that angle is very small, right? So it's rotating just around its stable point. Then cosine of a small angle is very close to 1. And then what you have when cosine of the theta is very small, so theta is much smaller than 1, then what you have is this is just G divided by L square root, which is exactly the same frequency as the frequency of oscillations of the pendulum. Right, so it's the pendulum will oscillate with exactly the same period as it rotates around on the same angle. All right, does it remind you of something? Come on. Does it remind you of anything? Of what? I need to increase the volume here. Yeah. So what does it remind you of? What again? Say it again. Well, yeah, it's that was one of the reasons for that. I was trying to make you think about three-dimensional motion. Right, so it's a hoop, and it's also that this is something which is required for Foucault pendulum, but it's actually there is a more straightforward example of the same kind, and that's, remember that the problem of Earth and the hole through it, and the time it takes to go from one end from North Pole to South Pole through, that the hole is the same as what a satellite would take. Right? That's exactly the same thing. And the reason for that is exactly the same, because remember that when a particle goes through the hole, it's actually an oscillator, and so linear oscillator will they all have that kind of property, right? So you see that there are some connections between problems which actually good to understand. All right, so that was the first problem, and the second problem was the one with that hoop, rotating hoop, and you needed to compute the frequencies of oscillations, small oscillations around the minimum. For both cases, when omega is larger, so you had a hoop, right, and it's rotating around this axis with the frequency omega, and there is a beat here, and you need to figure out what is the frequency of oscillations of the beat around its minimum, around its equilibrium position in both cases, when omega larger than omega smaller than omega critical, and omega larger than omega critical. Right? Now that's actually a trick problem, not a tricky, but a trick problem, because it's actually solved in my lecture notes. If you just read my lecture notes, there's answers for that, and the solutions are written there. I didn't explain those solutions well during the lecture, simply because I didn't have time. But it's all written there, so all you need to do is to take my lecture notes and actually understand how it's done and do it. But without it, you can if you remember from the lectures, the equation of motion which was derived in the lectures was like this: that this angle, the dynamics for this angle theta, which is the only parameter in the problem, is the following: that it's omega squared minus times cosine theta minus minus g divided by r, right? Times sine theta. That was the equation of motion which was derived there. I wrote the Lagrangian and then derived that equation of motion from the Lagrangian. Okay. Now, instead of, let me simplify it a little bit, and instead of g divided by r, I would write here just omega critical squared. Right? That's what it is. So now I have only one parameter in the problem, that omega critical squared and omega critical, and then it means that I have one less letter to write, and it means that I have one less chance to make a mistake. It's always a good thing. All right, now you need to consider two cases separately. Omega is less than omega critical. That will be one case, and the other case will be omega larger than omega critical. In this case, we know that the equilibrium position theta naught equals 0. So all we need to do now is to take this function and do Taylor expansion around theta equals 0. Right? Now, when theta equals 0, cosine is almost 1. Right? So what we have here is theta double dot equals cosine is almost 1, so we can forget about it. And this is omega squared minus omega c squared. And the sine of theta for small thetas is the same as theta. So here's my equation. Now, looking at this equation, I see that this is the case when omega less than omega critical. So this is a negative number. So in order to make it a little bit easier, I will write it as a positive number with putting minus sign in front and switching the order. Right? And now what we see here is standard oscillator equation. And so that the frequency of oscillations equals square root of omega c squared minus omega squared. Right? That's all for this case. Now this case is a little bit more complicated. But here we know that cosine, the equilibrium position is given by cosine theta naught. And that equilibrium position is when what's inside here is 0. All right. So it's cosine theta naught equals omega c squared divided by omega squared. Right. Now we need to take this function and use a Taylor expansion of this function, whatever is here, around this point. Right. So we need to first we have this function. Just consider it as function of theta, and we need to use a Taylor expansion around the theta naught. So the first term of any Taylor expansion is the value of this function at theta naught. If I substitute here theta naught, I will get 0, because that's exactly where it comes from. Right? Because cosine theta naught equals omega c divided by omega squared. I substitute it here, I see 0. So the first term is gone, as it must, because otherwise it's not an equilibrium position with theta naught. And this is the next term. I need to take the derivative of this function. Right? And multiply it by theta minus theta naught. So what will I have is theta double prime equals. Now I need to take the derivative of this function. Right? So I need to write d over d theta. And then this function omega squared cosine theta minus omega c squared times sine theta. Right? And so I need to take the derivative of this function at theta equals theta naught. So what I need to do, I need to just take the derivative and substitute in this derivative theta equals theta naught. And then right here and multiply on this by theta minus theta naught. Okay? That's a standard Taylor expansion. That's the first term. After zeroth term, this is the first term, the first order term in Taylor expansion. So all I need to do now is to compute the derivative of this function and substitute theta equals theta naught. So let's do that. So I take the derivative. This is what is that? Product of two functions. So I know how to take derivative of the product. So what I have here, I need to differentiate first this one, and here is only cosine. So I have then omega squared, and the derivative of the cosine is minus sine, so it's minus. sine theta, right? That's the derivative of this function, and I need to multiply it by sine theta, so it's squared here, right? And then I need to write plus. Then I need to write just this function as it is, omega squared cosine theta minus omega c squared, and then differentiate sine theta. Derivative of sine theta equals cosine theta. Right? Now, after I've done this derivative, I need to substitute instead of theta, theta naught. So it's theta naught here, theta naught here, theta naught here. Right? And then, after that, everything must be multiplied by theta minus theta naught. Right? That makes sense?
Yeah.
That's how we take the derivative. But now, you see that theta cosine theta naught equals omega c squared divided by omega squared. So this term is gone. It's 0. And the only thing which I have is this one. Right? But instead of this, this is sine squared, and this is cosine squared. But sine squared equals 1 minus cosine squared. Here, right? And so it equals 1 minus, and now I need to take omega c to the fourth divided by omega to the fourth. Right? Right? So that's the sign. And I need to multiply by omega squared and put minus in front. So it's minus in front and omega squared. So what I have now is that if I plug everything in, all that I just write it easier way, I have here minus omega squared minus omega c to the fourth divided by omega squared times theta minus theta naught. And that's what theta. But now you see that instead of theta double dot, I can always write theta minus theta naught double dot. Theta minus theta naught double dot, right? Because it's double dot of theta naught is 0. It's a constant. So now I look at this, and again I see exactly the oscillator equation, and then what it is here is my frequency squared. So I have then omega equals square root of omega squared minus omega c to the fourth divided by omega squared. That's all. That makes sense? So now if you actually try to plot it, how that omega depends on omega, right? What you see here is there is omega critical where it is 0, right? When omega equals omega critical, it is 0. And here when omega equals omega critical, those power of 4 is cancelled by power of 4 divided by power of 2 will give me power of 2, and then I get again 0. So from both sides, it is a square root singularity which goes to 0. That's the frequency of the oscillations. Now how it goes to 0, it is square root, but what is in front of square root will be a little bit different. It's a factor of 2, I think, difference there. And square root, I don't remember. So it's easy to compute. But you remember that the frequency of oscillation is something which we can measure, even if we don't see that ring. We can assume, well, if you assume that this mass has some charge on it, then the frequency of oscillation is the frequency at which I have absorption, a large absorption of light. And what I then have is that I can measure that absorption of light frequency at which the light is absorbed, and I will see that it's when I increase the rotation, speed of rotation, it goes to 0 and then it comes back, and then I know that I went through the transition, right? So that's how you can measure that there is actually transition. And now there is another thing which is very, very important, in fact, that it actually goes exactly to 0 here. And going exactly to zero means that there is no more harmonic oscillations around this point, and in fact, it means that there is some emergent symmetry in the problem. And I'm not going to go into that, but it's a very important point to understand, for us to understand what's going on exactly at the transition point all around. All right, any questions? All right then, and let me then start with the material for today. So as I said, the last lecture was the previous lecture was the last lecture on mechanics and proper mechanics, and now we'll talk about some other stuff. But we will always use the ideas which came from mechanics, all the ideas of differential formulation of mechanics and those and everything of that kind. So I will try to show you that all of those things are actually can be used and are relevant and actually exactly the same as in standard mechanical systems. All right. So what is the theme of today's lecture is waves, right? So you all know waves, don't you?
Yes. Yeah.
What kind of waves do you know?
Sound waves.
Right, sound waves. What else? Say it again.
Light.
Light. All right. What else? Exactly. Yes, water waves. And well, then you can substitute instead of water any liquid, and it will be a lot of waves, right? There are lots of liquids. And so any liquid, any wave on the surface of a liquid or in between two surfaces, if you have, for example, oil and water, they don't mix, right? So there will be a boundary between them, and on that boundary, there also you can also set up waves inside this boundary, and so forth. So pretty much everything is then will produce your waves, and the same thing with the solids, right? If I hit this table, right, that sound which you hear is part of it comes from that heat itself, but the other part is coming because there is some waves propagating on the surface of the table or inside the material. And those are sound waves and their compressions and so forth. So it's a sort of common phenomenon, right? That wave, and plus light is wave, and we know that, and it's a big thing, right? Because that's all we see, right? You don't see objects, you see light which comes from that object. That's what your eyes are sensitive for. There is a sensor there, and if you open your eye and split it, you'll see that sensor there, and that sensor doesn't know anything about objects. It only knows something about light which comes into your eyes, and that's all it does. It just measures the light. It's actually spectral properties of light. So in reality, what your eye, for example, sees is not objects. You can think about it as you see objects, but it's not so. It's just because it's very difficult to separate an eye from a brain, right? They sort of stop working. And so what your eye sees is a bunch of color spots, bunch of colors which come in, and it can sort of judge directions. And because you have two eyes, you can actually judge distance to where they come from. But that's about it. And the rest of it is done by your brain. So what is the separation? What is which color point is what object is done by the brain, not by the eyes themselves. So in that sense, all your eyes are seeing is just light. That's it. And so the waves are then very important for our understanding of the universe, right? Of how our world is working, and for any aspects of it. There are lots of aspects which are described by those waves. Now, I want you also to understand another thing about the waves. The waves do not exist when you have just one particle. It's just one particle, point like particle. What is wave? There is no wave there, right? If you have 2 particles, there is no wave. If you have 3 particles, there is no waves. If you have 10 particles, there is no waves, right? So only when you have many particles, they collectively produce a wave. So in this sense, a wave is always a collective excitations of something. And so what it means is that if you remember that if you have any system, it will go down to its minimum potential energy or free energy if the temperature is not zero. So it will be at minimum energy. And then what you can do, you can disturb the system. You can kick it a little bit out of the equilibrium. That is called excitations. Right? We excite the system. We do something to it and it excites. And then those excitations propagate through the system by waves. Right? So in this sense, the wave is a propagation of a collective modes, collective excitations of particles which we have in a system. So what again, if you can think about it even more abstractly, you can think about it the way that when you have many particles, you have a large system, there is something else appears like waves, which does not exist for a single particle. Sure, the waves are eventually, that's of course if you zoom in, it's some motion of single particles there, but it can be described as a completely new phenomenon, as wave propagation. Right? And so when you have many particles, you have something more, something new in the system. And it's collectively all that kind of ideas are called were called by one of the greatest physicists ever lived. His name is Phil Anderson. His name was Phil Anderson. He died, I think, last year. And he's not very much known to the public as Einstein, but that's a guy of the same caliber. And once he wrote a sort of philosophical paper, and which I think it's even title says more is different. So the idea there, when you have many particles, many objects in your system, they collectively produce phenomena which do not appear at all on the level of a single particle physics. Right? And that's actually something which we see all the time. It's superconductivity, superfluidity, all that very nice, very interesting and intriguing phenomena. They come because of the collective behavior of the particles is completely different and actually almost cannot be predicted by if you know the properties of particles. It's very hard to predict their collective behavior. In principle, it should be possible because we know all the equations of motion, we know all the physics, we know everything which goes on there. But in reality, if you try to do that, I mean, you cannot write equations for 10 to 23 particles. Even thinking about it, it makes me sick. So you always have to find out some interesting features of the collective behavior of that system. Otherwise, you have no hope to describe it. So that collective behavior is of many systems is what is called condensed matter. It's actually what I do for living. I will accept teaching, and that's, in my opinion, that's the most interesting part of whatever human beings doing is exactly what I'm doing, right? Otherwise, why would I do that? And so it's how collectively simple things behave in completely different, in some sense, absolutely different. You cannot even imagine. I mean, a lot of those effects were found by accident in experiments because no one ever thought about it that it's actually possible for a system to behave that way, and so no one was actually looking specifically. It was always by accident. Like superconductivity, for example. Who would think that if you have many electrons and they actually can flow in a dirty metal, so there are a bunch of impurities inside, and so in the dirty metals they can flow around the circle, and that current will stay there forever. It will never decay. So I mean, the human imagination has its limits, and it's always the new experiments which like sort of extend our limits of those. And or there are some other experiments when collective excitations behave as if they have charge of 1/3 of electron. There are such systems. We can do them. We can produce them in the laboratory. Well, they require huge magnetic fields, very low temperatures, very clean materials. So it's not an easy experiment to do. But nevertheless, it's possible to do. And it shows some collective excitations which behave as if they are particles with a charge 1/3 of electron. Now, you cannot split an electron in 3 parts. It's impossible. I mean, it's completely out of question for any physicist. We for sure know that if such process exists, if the electron is not an elementary particle and it consists of something else, then in order to split it would require such a huge energies which are definitely not accessible to humanity right now, and probably never will. But nevertheless, it's collectively those electrons, collectively that sea of electrons actually behaves as if it is a particle of charge 1/3, and 2/3 go somewhere far away. And so it's something again, something which couldn't be imagined, and no one has imagined that. It was found in experiment, and then people started to think how to explain it, and now we have the theory of it, and the theory is crazy, and it's very, very beautiful, very interesting. Anyway, so those are collective excitations, and in this sense, the waves are the simplest of the collective excitations. It's something which we can actually describe quite efficiently. But what I want to emphasize is the waves is something which has very specific features, and those are features which I want to actually emphasize. So, what is a wave? A wave? Well, you all know that, right? Here's a wave, right? That's a wave. That wave has several properties. So let's say that this is our 0, and so you can think about it as a wave on the surface of water, or sound waves, and this is the pressure, ups and downs of the pressure, or light, then this is the electric field going up and down, and so forth. Any wave will sort of can be represented of this kind. So that wave has wavelength, right? So this distance in the real space, that distance lambda. It's wavelengths, right? Now, the waves usually propagate with some velocity, v, or let me call it c, just to be fancy, right? So if this is how it looks like in real space, if you had like sort of a special camera which can take a picture of the wave, and of course you can. I mean, if it's a wave on the surface of the water, you can just take a camera and take a picture, and then at this particular moment of time, that's how it looks like, right? But now let's imagine a different experiment. It's when you sit in here, and you observe that wave coming at you, right? And you can only observe what's happening right to you. So what you will see is that if it's sound, right, that the pressure goes up and down with time, right? And there is and it goes up and down, up and down, up and down. So there's some period of that oscillations, right? But then to make those two pictures consistent with each other, we should say that the period is exactly when wave traveled, it's traveling, right? You need to assume that it's just going, so the whole picture is going. That period is exactly when wave is traveling the time which it takes the wave to travel from this point to this point. So then, at this point, after that time, everything repeats itself. So that's a period, right? So it means that velocity must be equal. The velocity of propagation must be equal to the length which wave is propagating, divided by the time which it takes to propagate. Right? Does that make sense?
Yeah.
Now, time of the now usually we don't describe waves with the time, with the period. We describe them with frequency, but frequency is just 1 over period. So using that, what we see here is that the speed of propagation equals wavelength times the frequency. Right? So it means that if you know the velocity of the wave propagation, and we usually do, it's something which depends on the material, it depends on the nature of the waves, but we can write equations and do that. If you know the frequency, if you know the velocity of the propagation, and we know wavelengths, we know the frequency. If you know frequency, we know the wavelengths. Right? That makes sense?
Yes.
All right, but that's so it's actually a trivial thing. In fact, it's just a definition of different of what is what for description of the wave. And but it's very useful. It tells us how to compute things one from another. All right, but there is one thing which is sort of getting missed by a lot of people who, when they think about waves. Let me draw another wave, right? And that wave will have exactly the same velocity. Say it's a wave on the same material. It's the same kind of wave, and it will have exactly the same wavelength, right? But it will now look like this. Let me use some other color. No, tell me if you don't see it, that color. All right. Do you see this?
Yeah. Yes.
Yes.
So it is the same wave, right? It's propagating the same velocity. It has the same wavelength. So it will have the same frequency. And by our observations, you will not be able to tell one from another. So what is the difference between them?
You've shifted it.
Exactly. Exactly. Say again? Yes, exactly. I shifted it, right? So this is the phase. That's what is called the phase of a wave. I changed the phase of it, right? So a wave has two properties. A wave of given wavelength has two properties. It has amplitude, how much it's going up and down. So this is an amplitude. But it also has a phase shift. So if I try to describe it, the simplest function which looks exactly the same is the following. The wave can be described by amplitude and then say sine omega t minus 2 pi lambda divided by x. Oh, sorry, not the other way. X divided by lambda. Okay, so that would be normal description of a wave. That omega is 2 pi phi. It's just I like that better, so I don't need to write 2 pi all the time. So what now? Look at this. Look at this function. It has all the properties which we need. All right. The waves can be very different. It's not necessarily described by this, and I'll talk about it a little later. It's not necessarily described by this function, but it's the simplest function which has the same properties of the waves as the waves, right? So if you look at this, if I now look at the same point, right? I'm sitting here, and I take time and add to it 2 pi divided by omega, right? Instead of I'm observing it at time t and observing it at time t plus 2 pi divided by omega. Then if you substitute it here, you see that in this term the omega will cancel out, and what I will have is just 2 pi, right? But sine of 2 pi, if I add to argument of sine 2 pi, I exactly get the same number. So it's 2 pi is the period of a sine, right? So it means that everything, when I observe it in one particular space point x, right here, I'm sitting it, observing this wave coming to me, then what I will have is some periodic function with the period which is 2 pi divided by omega, and that's exactly the same period. That makes sense?
Yes, it is.
Or I can do different story. I can say that I fix time. Remember, I'm taking like sort of photograph of it. And so I fix time, and then I change at what position I'm observing that way. And then what I see is that if I take x and add to it x plus lambda, right? Then what I will that lambda will cancel this lambda. I have just one. It multiplied by 2 pi. It will give me 2 pi shift. And so it again returns back to where it was, because it's again sine and argument is you add 2 pi to the argument, right? So it means that lambda which is here is exactly the wavelength, right? Does it make sense?
Yeah.
And now you see that this a, what is here, is exactly the amplitude, because the largest value sine can have is 1. So that function, the largest value it can have is a, and the smallest is -1 for sine, so it's -a. So it goes from +a to -a. So this is amplitude, right? But as I said, there must be also phase. And so in order to do that, what I need to do to this function, I need to add a phase here. Right? And that's also that phase shift which I have, that shift of the total thing. And you can see it right away from here, because what is written here? I can always write it the same in this argument differently. I can write it omega t minus, then I have 2 pi, right? And then I have x minus lambda phi divided by 2 pi and divided by lambda, right? So I can write it, the argument this way. It's exactly the same function, right? You see that lambda cancels this lambda, this 2 pi cancels this 2 pi, this minus cancels this minus, and what I got eventually is just phi, right? But what it also tells you that the change of that phi is just the change of the shift of the wave. So I just shift x by this number, and that's my phase shift. Does that make sense?
Yes. Yeah.
So that's exactly what you answered. That one wave different from another by phase shift. Or I can do it another way. Think about it. If I'm now here as an observer, and I'm looking at those two waves, that this maximum will come a little bit earlier to me than this one, right? So as an observer here, I don't see, I look at a time picture, and the phase shift in time picture means that one wave, the maximum of one wave arrives a little bit earlier or later than the other one. And again, it can be seen exactly the same way, because that argument I can rewrite as omega t plus phi divided by omega minus 2 pi x divided by lambda. Right? That's the same argument. If I multiply omega here, you have omega t, and this omega cancels this one, and I get just plus phi. But that means that I just shift my time. So I just started my watch a little bit later, a little bit earlier, but there was a sine phi. Okay? Does that make sense?
Yeah.
So, but then what it means is that, remember that when I started my watch, or how I measure the length, and from which point. So remember that shift, it means that I shifted the wave, or I can actually shift my system of coordinates. So the numbers will be exactly the same, right? It's equivalent things. And the same thing, I shift. That wave came a little bit earlier, or I just started my watch a little bit earlier, or a little bit late. Sorry, right? It's the same thing. So what it means is that phase, when it is here, it has no physical meaning whatsoever, because it actually fixes when I start my watch of what is the origin of my system of coordinates. All right? That makes sense?
Yeah.
So when I have a single wave, that phase has no physical significance, because that phase only shifts my time or only shifts my system of coordinates. And that's it. That's when I have one wave. But if I have two waves, right? So the next wave is b times sine. The same thing, omega t minus 2 pi x divided by lambda, plus some other phase. Then it means that one wave is shifted with respect to the other. And I cannot compensate for that shift for the difference between the phases by changing my origin of coordinates and the origin of time. Okay? That makes sense?
Yeah.
So I can change this phi. I can change this theta by changing my when I started my watch. Right? So I can change both of them, but I cannot change the difference between them, because the difference between them is the time connected to the time when I'm observer, connected with the time when I observe this maximum with the time when I observe this maximum, and this is a time difference. And time difference does not depend on when I started my watch. Right? The same thing with the length. That constructing that phase, putting it back in length, then the phase tells me what is the length between one maximum and another maximum when I just taken a picture of it at one single time of two waves, right? And that length, the difference between the 2 points, does not depend on where I started to measure my coordinates from. Right? So the phase difference has significance, tells you something physical. The phase itself is completely insignificant, but the phase difference between different waves is actually very, very physical. All right? That makes sense?
Yes, it does.
All right. So next important thing about so what it means is that all that waves can be described by the amplitude, how much it of it, how big it is, right? And the phase. And out of those two, the phase actually has more significance than amplitude. In fact, the phase is what distinguishes the behavior of waves with the behaviors of particles. And I'll talk about it a little bit later, a little bit more. So it's the existence of the phase, which is very, very, very important for the and very significant for the propagation of waves and to distinguish waves to particles. So let me then let's move on. And now there is one more thing about waves which is quite important. It's typically waves. When we talk about waves, when we have linear problems, it's I mean, why it is so? It's a different story. It's not necessarily, but majority of the time it is so. And then what we have is that we always, because it's linear equations which we solve normally when we try to describe waves. So what we have is a principle of superposition. Namely, if I'm observing here, right, the disturbance. Let's say that I'm listening those two sound waves which are coming to me, and I'm just listening to them, right? It's I close my eyes, I don't see the waves, right? You don't see the sound waves, but you can see, but you hear them. So what I'm observing here is the sum of two waves. So if I have two waves coming in, so one wave of x and then t, and the other wave, and I'm sitting on the same. So this is F1, this is F2. So what I observe is the sum of them. Right? It's two waves coming to me. I'm just looking at that simple sum of those two waves. All right. So so that is called principle of superposition. Right? So I just simply sum up two waves. Again, this is not necessarily so. It's the simplest thing to do, but it has to be checked experimentally that it can be done because it follows from nowhere that I can do that. I know how to mathematically how to get it because I already know how the theory is constructed. If I don't know the theory, there is no a priori way to say that I just sum them up and that's it. That's my answer. It can come with many complicated ways to combine two functions into one. But for waves, it's a principle of superposition. It's what is called principle of superposition, and it comes because of the linearity of all the wave equations. And we will only use linear wave equations. In particular, that's can be. We can explain then the following phenomena. It's let's imagine that we have two sound waves, right? Two sound waves coming in, but they have a slightly different frequency. You remember the frequency of the sound wave is the pitch of my voice, right? I can talk low, I can talk right, and it's different frequencies of the sound which I can produce. And so then what you have is, let's say that there is one sound wave, and let's forget about amplitudes. Let's say that they have the same amplitude. So if I'm sitting on one point somewhere, right, and so I have two waves now coming my way, and I'll forget about the phase shifts right now because it's just makes calculations a little more complicated, right? But doesn't change. So there is two waves, but they have a little bit different frequencies. One is coming with frequency omega 1, the other is coming with frequency omega 2. Then, according to principle of superposition, that's what I hear. Right? Well, it's a little bit more complicated. I hear the square of this, but it's okay for now. It will be important later on, but for now it's fine. So what I then so that's what I hear, right? But there is trigonometrical formula which tells me that those functions can be identically written in different way. It can be 2 times cosine omega 1 minus omega 2 divided by 2 times time, and times sine omega 1 plus omega 2 divided by 2 time. This is trigonometric identity. It really doesn't matter how to write this function as sum of two sines or a product of cosine and sine. It's the same thing. Okay? But the way how you that formulas have sort of different way of looking at them. And specifically, I want to consider the situation when omega 1 is almost the same as omega 2. So what it means is that if I take omega 1 minus omega 2, they have almost the same frequency. That the difference, the absolute value of the difference, is much less than say omega 1. Okay? Then what will I have here? I have here omega 1 plus omega 2 divided by 2. But that's about the same as just one omega, right? Because they're pretty much the same. What it tells you is that they're very, very close to each other. So then, in this situation, what I will have is I have here just omega t. Omega is either omega 1 or omega 2. It really doesn't matter. They're very close to each other. But here, I have the difference between them. They're close to each other, but they're not identical. So I cannot write 0 here. Right? I have to keep it as it is, because it depends exactly on the difference. But now what I do know is that this frequency is very, very small. Divided by 2, right? It's very small, right? Very small frequency, it means that the function is almost does not change. So this is a very slow function, and this can be very fast in comparison to this one. So I have a product of very slow function times very fast. Then I can think about it differently. I can think that this is my oscillating function, which oscillates very, very, very fast. And this is just an amplitude of this oscillating function, which slowly depends on time. So amplitude slowly depends on time. So and then if I draw this, so this is my time, and this is the sum of the two functions. Well, I first draw the amplitude like this, right? And this is my amplitude, and on that amplitude I have this function, which has this fast oscillating function, which has this amplitude. Like this. So that will be the picture, right? Of two sound waves coming with almost the same frequency. So what I will see then is that I will have, for example, if it's a tone, right, of the frequency is just a tone on which you hear. So I will, if I have two sources with almost the same tone, what I will hear is that tone which they're almost the same, so I cannot distinguish between them. But the value, the how loud the sound is, will depend on time. So it will do something like wow, 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 wow. Right? That's exactly what we will do, because that's exactly what I do. I'm giving one tone and I modulate its the strength of that tone. Does it make sense?
Yes.
Yes.
So if you ever tune the guitar by ear, right? What you do there? You take one string, what is fifth fret, right? And the next string, and then that picked string will produce the same tone, right? On the guitar, is it correct? Come on, there must be guitar player around there.
Yeah, that's right.
Same thing as violin or anything, right? So it's and then what you hear when you're tuning it, what you hear is that when the sound which came into you does not have those beats, right? That's exactly when they're in tune.
Right.
But that exactly means that no beats. It means exactly that omega 1 equals omega 2. And when omega 1 equals omega 2, cosine of 0 is just 1, so you have exactly the same amplitude, and amplitude does not change with time. So that's exactly the superposition of sound which you actually use to tune your guitar. Does that make sense? That makes sense. All right, good. All right. So that's one thing about that the nature of waves. And another thing is that, those are two waves of different frequency. So let's now think about two waves of the same frequency and the same wavelengths. And again, I can have one wave and another, right? So let me say that I have one wave like this, right? But the other wave which I have will be like this. Notice that it's the same wave, it's just shifted a little bit. It's shifted by exactly half of the period. Right? That makes sense?
Yes.
Yes.
But now if I sum those two, I will have 0, right? So because here's my 0. So you know that's supposed to be 0. So if I sum those two, this will sum up with this one, and it will give me 0 everywhere. So I do have some two waves coming to me when I'm sitting here. That's me. But I hear nothing because those two waves actually cancel each other. Right?
Right.
So they come out of phase, and this is called destructive interference. Or I can have a different situation, and I have two waves. One is a white wave, and the other now will be a red one, and they're almost the same, right? So they have almost the same phase, like this. Then when I add them up, I just double the amplitude of my wave, the total wave. Now that's not the end of the story. The power of sound which I hear is actually not proportional to the amplitude. Remember, there is amplitude of the wave. It's not proportional to the amplitude, but it's proportional to the square of the amplitude. That's how it's always done with waves. So if I double the amplitude, my power which I hear actually multiplied by 4. So this is called constructive interference. So two waves can interfere with each other. They can either cancel each other or magnify each other, in fact, right? And that's just because of the superposition principle and the fact that there is a phase in between those two waves. Okay, and this is something which distinguishes waves very strongly from particles. Particles cannot interfere and cancel each other. When two particles are coming, this is two particles that are coming. That's it. Right? They can come differently, they can collide, but it will be two particles which I will measure. Now with waves, if I shift the phases, if I adjust the phases correctly, it can turn out that there is nothing coming my way. And I hear nothing. Okay? Or it can multiply each other. So that phase, the fact that I can make a phase shift and do something and completely change the result is actually what distinguishes waves from particles. Or in other words, waves from, say, particle stream. Right? You can think about that waves are very different from particles because waves is like sort of everywhere. It's coming piece by piece, right? And particles just coming in one point. But if you think about that stream of particles, like stream of water, which come in your way, right? And some sort of a wave, and you just measuring the power which comes to you. That there will be no distinction between the stream and the wave coming at you, unless you include phase into consideration. And then when you have two waves or two streams, when two streams coming at you, they're just two coming at you. That's it. Right? When two waves coming at you, they actually come in such a way that they cancel each other. Or multiply each other, magnify each other. So it means that's fact that there is some internal degree, freedom, that phase, there's the phase shift between different waves, and it can completely change the result. That's what distinguishes particles from waves. Okay, that's the phase shift, which is the most important one. All right, so let's move on then and say that how do we describe now? I draw it in one dimension, right? Everything, but in reality, we live in 3 dimensions, fortunately, and it's the wave propagates in 3 dimensions. Well, 3 dimensions is hard to draw, so let's think about the waves on the surface of water. Then you all know, right? If you drop a stone in the water, right? So what you will see is those waves coming out, right? Oh, let me just draw it. Does it look familiar?
Yeah.
Have you dropped a stone in the water? I hope so. So those waves are coming out. Now notice that what I'm drawing here. If you look at this, typically you draw here the maxima of the wave, right? If I now take this cut of the wave and then sort of turn it around, what I see is a wave just coming this way, right? And what's the lines which I draw here is the lines of a maximum, right?
Right.
But the maxima is exactly the points where if I call it, if again use sine omega t minus 2 pi x divided by lambda, right? Those maxima is exactly the same, the place where x changes by lambda, right? And if x changes by lambda, then what's inside here changes by 2 pi. Now, changes but 2 pi means that the phase is defined only up to 2 pi. Remember that there is a phase here, right? And phase plus just add 2 pi inside the sinus and nothing changes, right? It's a periodic function. So the phase is defined up to 2 pi. So the total argument is defined only up to 2 pi. And that's exactly what it is here. So if you take the definition up to 2 pi, mathematicians call it modulo 2 pi, then what we have here is that argument of the sign is on this point is exactly the same. They distinguish only by 2 pi, so it's exactly the same argument, right? So what you draw here, that lines which you draw here, is the lines where the argument of whatever the function describing your wave propagation is changing by the period, by 2 pi, you say. And if you say that phases which are distinguished by 2 pi is the same phase, then what you draw here is the lines of the same phase. Meaning that if this is maximum, this is maximum, this is maximum, the same phase of our wave, right? So lines of the same phase, when you have propagation in 3 dimensions or 2 dimensions, lines of the same phase are called what is this called? Wow. Front lines, right? Wave front, sorry. I'm getting older. So those lines of the same, or surfaces in 3 dimensions, this is surfaces, right?
Right.
So those surfaces on 3 dimensions, on lines, or in 2 dimensions, are called wave fronts. It's a surfaces or lines of the same phase. Does that make sense?
Yes.
So this is just a way to draw the propagation of waves. All right. So that's sort of clear picture, but now I want to contrast it with a different picture. I want to remind you that there is another that the light is also a wave, right? So the light is propagating and it's a wave. So, but remember that you probably studied optics at some point, right? So it's in some of the introductory physics we have optics, and in optics you use rays, right? So there is a ray. There's like this lens and then there's rays coming in. And there's a focus and focal distance, blah blah blah, all this stuff about geometrical optics, right? So when you describe, when in this situation, when you describe propagation of light, you describe it with rays, right?
Yes.
Moreover, even when a little kid draws it, like a sun, right? Here, how that little kid draws the sun, right? So this meant to be rays of light. So where is those rays? We have waves propagating. What are the rays here? Do you know?
Well, they're particles, aren't they?
No, it's light. Light is wave.
Well, that's the thing about light, isn't it? Both a particle and a wave?
Do you really know? Do you really think that little kids know that? And they draw rays. And moreover, that principle tells you that those things are exactly equivalent, right? It's not like it's standard misunderstanding that people think that light can be wave or can be particle. It's not so. It can be described as a wave or it can be described as a propagation of particles. But it is the same thing, and just different point of view on the same phenomenon. It's a way how you describe it. It's not what it is. All right. So those two ways to describe it are absolutely equivalent. That's the statement. You can describe it as propagation of waves. You can describe it as propagation of quantum mechanical particles, and those two descriptions are absolutely identical. Okay. So it means that if we can describe it as waves, there must be some rays of light there built in. Because it should be equivalent. We should be able to transfer from one point of view to another. We can describe the same thing either through propagation of waves or through propagation of rays. So where is the rays here? Do you know?
I mean, you can make a line with like a superposition of multiple waves.
But that's all I have, right? I throw a stone and the waves coming out. There's only one wave. All right, so I'll tell you that construction, actually. There are rays here. So you see that those are wave fronts. Now what I want to draw a line which is perpendicular to the wave fronts at every point. Here, because it's a circular, that will be the line. This is my rays. Right? So if I know the picture of wave fronts, I immediately can reconstruct the rays. If I know the picture of rays, I can just draw surfaces which are perpendicular to the lines. For example, in this case, I know what the rays doing, right? So I can reconstruct what the wave fronts are doing. The wave fronts are here; they parallel to each other. They come into this length, and then they get bent like this. So those are my wave fronts. They come in and then they go like this. Okay. So the ray is a line which is perpendicular to the wave front. That makes sense?
Yes.
Now, it is a wave front which is moving with the speed of whatever of those waves. That wave front, right? This is a maximum. The next point of time, that maximum will be somewhere here, and that distance will be the time times the propagation of the ray, of the wave, right? Now, notice that when you're talking about rays, there is no speed. It's just pure geometrical construction. The speed is hidden in fact that there are some wave fronts, and those wave fronts propagating. So they come in like this, and they propagate there. So that picture is actually very constructive. So let me show you how you can use it to actually do something. So let me imagine that I have pink region and blue region. And my wave is propagating with different velocity here and here. So the velocity here is Vp, the velocity here is Vb for propagation. All right. So I want to, but now let's say it's light. All right. So light is coming in, and I know that it should bend. But notice, so that ray of light should bend, right? The ray of light should bend like this. Right? It's a snail's law, it's what it is. But then it's always a puzzle when you talk about the whole thing this way. It's a complete puzzle because the ray knows nothing about the speed of propagation. It's just a line. Right? There's nothing propagating here. So how come that the ray depends on what is the speed of light in two different areas? And that becomes absolutely clear when you understand that that ray, that line, is just a line which is perpendicular to the wavefronts. So let me say that so I have wavefront here, right? So this is my lights, this is rays coming in. I hope they parallel, right? So eventually that wavefront, there is wavefront over here, and it's perpendicular here, right? And then there is a wavefront, and here I have another wavefront which are coming like this. So this is my wavefront which is coming right from here, from this point. And this is also perpendicular. And this one is orthogonal perpendicular, right? Does that make sense? No, that's light which is propagating. This is propagating through media, and that light has velocity here, VP, velocity here, VB, right? So we know that it must bend. This is a ray of light. You can think about that. This is the ray of light. I'm just looking inside. So this is a ray of light, right? So there is a ray of light, and it's a wave. Light is a wave. There must be wavefronts, and then those lines are wavefronts. This is the equivalent to the wavefronts, which is like those propagating circles, right? But I don't need to know that. I know that there must be there. Because it's a wave, and this is a ray, and wavefront is something which is the surface which is perpendicular to the ray. That's all. So there must be some rays like this, right? So now this is wavefront like this. So this wavefront is propagating and eventually becomes this wavefront, right? But in order to do that, this end of the wavefront must propagate this distance, right? And this end of this wavefront must propagate this distance, right? But this wavefront, this end of the wavefront is propagated in the pink region, but this part is propagated in the blue region. Okay? So let's then compute it. What we have here. Let's say that this distance is L, right? And this angle is actually the same as the length of incident, right? So this is pink angle, this is pink angle, and then this one is blue angle. Interflow, right? It's this and the same as this angle, right? So then this length is L times sine theta p, pink, right? From this triangle. And from this triangle, this length is L times sine theta b. Right? That makes sense?
Yes.
So that point of the wavefront propagates to here, up to here. It takes time, L sine theta p divided by Vp, right? That's the time to propagate of the wavefront from here to here. The time for the wavefront to propagate from here to here is L sine theta b divided by Vb, right?
Yeah.
But they must be equal to each other because that's the same wavefront. It propagates, and it becomes this one. So those times must be equal to each other. And you see that L cancels out, and you see exactly Snell's law. Okay? Does that make sense?
Yeah.
So you see that ray is just telling you sort of a direction. It's just a line. But the wavefront is something which is really propagating through the media. Okay, that makes sense?
Yes, it does.
All right, so that's the origin of that Snell's law, and you see that it's exactly the way of describing that the way how things propagate and how waves propagate. Now there is another way to describe it actually, and it's called Huygens principle or Green's picture, or depending on what school you go to, with which country it will have different names. But it's a very interesting story, and it tells you that mathematically what you can do, you can think about, let's imagine this is our wavefront at some particular time, and we want to construct a wavefront in the next time. You remember that this is the time t naught, right? Time t naught, and I want to construct the wavefront at t naught plus some dt, very small increment of time. So how to do that? I want to do it sort of locally. I don't know. I know only this wavefront. I don't know where it comes from. I really don't know anything else. I only know this wavefront. So how do I construct this the next wavefront? And it turns out that what can be done, it actually can be done mathematically. It's very well behaved, very established procedure. It's called green functions. But physically, it means what the following thing: that let's imagine that this wavefront now is a set of point-like sources of light. Very small, right? So they make light, but that light is coming in the same phase, because that wavefront is a line of the same phase, right? So each of those sources produces light with the same phase. So light from that source, the point-like source, will look like it just circles, right, or spheres. It's just the same as dropping a stone in the water. So they will produce all those little sources, will produce those bunch of wavefronts, right? And then I just sum up those wavefronts, and it turns out that they will cancel each other. They will interfere destructively everywhere except where I need where the next wavefront is. Then they will actually interfere constructively. So that can be shown mathematically. It's a bunch of equations. It's again, it's a consequence of the Green theorem. But nevertheless, that's sort of a picture which you can always reproduce next wavefront out of the previous one. Okay. So in particular, what you can do, you can say that let's imagine that I have a gap like this, a screen with a gap, and I shine a light on it. So the light is coming this way, right? And then what I have, what is light? Light is coming this way. It means that there are a bunch of wavefronts which come in this way. There's the flat planes like this, and they come here, right? And they get absorbed. The light got absorbed by the screen, and I have just a wavefront which is right here. Okay. So I want to know how it propagates further. And according to Green's picture of Huygens principle, I need to think about it as a bunch of point-like sources and just draw a wavefronts from each of those sources. Right? So it will look like this. This is a wavefront which coming from this source. This is a wavefront from coming the next one. So I do it like this, right? And then, so my resulting wavefront is this one. The sum of them like this, right? And then next point of time, I need to think about it as that wavefront as a collection of sources. And I again do this. Right? And this will be my wavefront, new wavefront. Okay? And now I can draw rays. Right? Because now I can draw the, so this is my wavefront, this is my wavefront, and now I can just draw the rays of light. So for example, this ray of light is coming through the center, right? It's going perpendicular, and it keeps going. No problem, because it always goes like this. But now let's think about this ray of light. It's coming this way, right? But then I need to start drawing lines which is perpendicular to the wavefronts. It goes like this, right? And this one goes like this. Okay? Does that make sense? Come on, that makes sense from the pictures.
Yeah.
So you see that wavefronts tell you the propagation, and then you can, after you know the wavefronts, you can draw the rays of light. So what it means is the ray of light comes in, and it actually bends over. Okay? So what it means also is that you can see behind the corner. The light will bend over the corner, right? Surprisingly, it does do that. And you can do the experiments with that. It's actually, I usually show that experiment, but if you have a laser pointer, let me describe it. It will not be seen here. Unfortunately, it's a very weak laser pointer. pointer. If you have a laser pointer like this, right? You take a piece of paper and you cut it, just like, I don't know if you can see it, just like here. You see that little cut, right? And you shine light through that cut from laser. Then what you will see, you see that my cut is going vertically. If I shine light on it and through that cut, I don't know if you see this. You probably don't. But what turns out that the spot of light actually has this shape. And if you look close enough, it actually has dark fringes and light fringes. But it has this shape. But my cut is vertical, but the light is going horizontal, elongates horizontally. That's exactly that diffraction. So this is my cut, and this is the screen, and it goes, it sort of spreads out. Okay, but it also tells you that the light is bending over around the corner, and it does do that. Okay, does that make sense? So this is called diffraction, and this is the most important part about the waves. They do diffract. And the idea of the diffraction, again, it's sort of it's the same as in interference, right? It comes because there is phase. Those wave fronts are the consequence that there is a phase in light, and the diffraction is the diffraction pattern is the consequence that the light is propagated by wave fronts. So diffraction is actually telling you that there is some phases in your system, all right? So that's one thing. So that's what waves do. It's everything which has diffraction, that kind of patterns. It must be a wave. That's how we distinguish wave from say streams of particles. Okay. There is some other things which you can do. Let's imagine that we have two mirrors. And we have light with some particular frequency inside. We try to make it inside. Then the light, well, you can think about it. The light is propagating to this mirror, this is propagating back to this mirror, this is propagating, and so forth. It goes back and forth, right? It's a ray picture, but the ray picture is incomplete. We need to think about phases, right? And interference. That light which is coming this way will be interfering with the light which is coming back. Will be interfering with the light which is coming back in, and so forth. They will always interfere with each other. And sometimes they will interfere destructively and sometimes constructively. Right? And if they interfere destructively, you do not see the light inside this cavity in the resonator. And the condition for that, for constructive interference, is that you see that it's very easy to understand if you think about it as a wave. So if the wave comes here with 0 and comes here with 0, right? So there is actually the integer number of wavelengths in between those two lines, right? So if this is the length of my resonator and the wavelength of my light is lambda, then if L equals n times lambda, then the wave which is coming back and forth will be exactly in phase with itself, right? And so it will always stay there. But if that relation is broken, then eventually, every time the light goes back and forth, it requires a little bit of a phase shift, and eventually that phase shift will become pi, right? And then you just destroy. They will interfere destructively, and they will destroy. So the light can exist inside that resonator. That's why it's called resonator. The light can exist inside this resonator only if we have this relationship between the length here and the wavelengths of light. Okay, does that make sense?
Yeah.
Again, this is a property of light. Because you can think about if it is a particle, it just goes back and forth and it doesn't care about what kind of length it is. But for light, it cannot exist inside the resonator unless there is this relationship. If you try to put a light which doesn't have this relationship with the length of the resonator, it will not go in. It will not be able to go there because it will interfere to zero, and it means that it reflects completely out of the resonator. That's one thing. The other thing, if you think about that little tube like this, right, and let's say that those lines inside this tube are mirrors, and you try to put light inside here, then that light which will be propagated inside, right? And again, if the interference is, if the condition of interference is not met, then that light will not be able to do that. It will not stay inside. You will not be able to put it in there. Only the light which has exactly the integer number of wavelengths on this on the whole perimeter will be able to survive in this cavity, and it actually will stay there forever if your mirrors are ideal. Okay, so those kind of interference patterns which are used all the time for all the resonators and everything, but it's actually so. And again, this is a consequence of a wave nature of light. So all the waves will do that. You can always build such resonators for any waves whatsoever. Well, they can be absorbed. Light is easier to build mirrors for. But nevertheless, if you have ideal situation, you can always build those resonators for any kind of waves. Because the only thing which is important for them is the fact that there is a phase. Okay? Did I already tell you that the phase is the most important part of light? Oh yeah, a couple of times ago. And the phase is most important part of waves. That's what distinguishes wave from particles. Sorry, it's my phone. All right. So let me then tell you something else about. I have to do that. It's important. I'm sorry. I'm taking a couple more minutes from more. So what I'm going to talk about, the last effect which I want to consider is the Doppler effect. So what it means is the following. Let's imagine that we have a source of light, or not light. Sorry, this light is different. Source of sound. Well, I'm talking only about acoustic Doppler effect. With light Doppler effect, we will talk about it later when we write the equation of propagation of light. But the sound is so there is air, right? Otherwise, sound does not propagate, and the sound is propagating. This is a source of my sound, and here is me sitting here and listening to it. And this is a source, right? And so it produces sound with frequency or tone, right? Which I will call the F source, right? The frequency of the sound which is produced, right? But now what I want to do, I want to say that this source is actually propagating towards me with velocity v source. Okay? And I'm sitting here, and the question is, what kind of frequency will I hear? Do I hear the same frequency or I hear some other frequency? And the question, of course, I hear some other frequency, and you can hear it yourself when somebody is honking in a car and the car is passing by you, right? You see that it's higher in tone, and then when it goes away, the tone becomes lower. You can actually hear that, and so this is called Doppler effect. And again, how to understand it is, again, it's very simple when you go towards the picture of wavefront. So let's imagine then at time t, right, that there is a wavefront here, right? Then the wavefront is propagating. So that source of light emits sounds, and the wavefront at this particular moment of time, the wavefront is here. After some time, some time delta t, right? That wavefront is propagating over here, right? And that propagation is that length which is propagating, will be equal to delta t times the velocity of sound in the air, right?
Right.
So now let's take time delta t to be the period of our oscillations for the source, right? So that time delta t then is a period, and then delta t then equals 1 over fs. Right? That's exactly the period. So at this, after that time, what I have is that wavefront propagated from this point to this point by distance c divided by fs. Right? So after that time, a new wavefront appears. Right? A new wavefront appears here. So this wavefront propagating now at this point of space, but a new wavefront appears. But it appears where that the source is. During the same time, the source propagated, moved some other distance, and that distance is the velocity of my source divided by fs. Right? Because the time delta t is 1 over fs, velocity of the source vs, so the distance is velocity times delta t. So my previous wavefront is here, right? Here, and my wavefront after time delta t is over here. So this distance between the wavefronts is c divided by fs minus v source divided by fs. And now those two wavefronts are propagating towards me. So I see one wavefront and then the other wavefront is coming. And the time difference between them is the period which I hear. Right? So the time difference between them will be c divided by the frequency which I hear. Does that make sense? This is FO, observer frequency. Right? So now I just do simple algebra, blackboard algebra, and write it this way. And now after that I invert those two formulas, and what I have is frequency of the observer equals c divided by c minus vs times frequency of the source. Right? That makes sense?
Yep.
So you see that velocity here, if velocity is towards me, towards the observer, then what I have in numerator is larger than what I have in denominator, right? So this is larger than 1. So the frequency which I observe is larger than the frequency of the source. Larger frequency means higher tone. So when the source is coming towards me, I hear the higher tone. Now, if the source goes away from me, all I need to do is to change the sign of the velocity here. Right? And then I see that this becomes less than 1, and what I hear is a tone which is lower than the real tone of the source. Okay? So that's what happens when car is passing by with honking at the same time. Does it make sense?
Yeah.
So this is Doppler effect. And now, last more thing. It is extremely important for that Doppler effect to understand that the sound is propagating through the media, through air, right? So there is a media, there is air, and sound is propagating through that, and that velocity of sound is the velocity of the propagation in the frame of reference of that media, right? Of the air. If air is moving, the sound will move with it. If you all, two of you are sitting in a car and you're talking to each other, that sound between you, the air is in the car is moving with you, and the sound is also moving with you. So it makes no difference, right? So it's very important that for this Doppler effect, it is very important to know, to understand that there is media through which the sound is propagated. All right. It will be important when we discuss the same Doppler effect, but for light. So I want you to remember that here media was important. All right. Sorry about taking a little bit more time, and that's it for today. Any questions?
You said the median is important?
Media through which the sound is propagated, the air or water,
Okay.
whatever sound is propagating through. So there is something through which sound is propagated. That's very, very important for here. Otherwise, I cannot say what is the velocity of sound is. I need to measure it with respect to something, and I measure the velocity, sound velocity, with respect to the media at which it propagated. Right? So I measure the velocity of sound in the air with respect to the air in which it's propagated. If the air is moving, the sound will be moving with it, and you can hear it. You can talk to people in a car, right? So the air in the car is moving with you, and you can talk to them. The sound is propagating through the same air, right? Does that make sense?
Yes.
All right. Any other questions? All right, that's it then, and thank you for coming. See you on Monday.
Thank you.
Good. Thank you.